Okay, welcome everyone to the last session of this lecture. So, since it's the last one, and I wanted to finish with something cool, then there is a little bit of a question maybe to deal with. So there's kind of two possible things that we can do. So recall what we have done so far. We have talked about symplectic reduction and about coisotropic reduction and Hamiltonian reduction. And then last time, which was 2 weeks ago, we talked briefly about Courant algebra reduction, which I just sketched, and then I said that we will now see that it's in particular a special case of Hamiltonian reduction, but done in the graded symplectic setting. So one possibility would be to elaborate on this and to show you kind of more details. So you will have to remember how this correspondence between Courant algebra and graded symplectic manifolds, how did it go, and then kind of see what is the thing that plays the role of the algebra here, or the group. The other option would be to just accept what I just said, that it works, and then we can talk about Poisson-Lie T-duality, which is like a relation of all this framework to kind of string theory, and like I have prepared more on the second one, so. And I think it might be more interesting. So is everyone fine with that? Okay. If there's going to be lecture notes, which there ultimately will be, then everything will be covered in there. Also, there is some papers which have content. Okay, so well then, let's change gears for now a little bit and let's talk about Poisson-Lie T-duality. So, this thing sort of originates in Prague, actually. That's right? Yeah, so
maybe he was maybe in Prague and CERN.
Yeah. Prague and Switzerland. CERN. So, Klimčík Ševera in the 90s discovered there is a version of the story of T-duality in string theory. There is a sort of non-Armodian version of that story, which is kind of interesting, and it's related to Poisson geometry. And it has been developed in physics. There is also some aspects of it which has been developed very much in math. And so I will focus on one particular incarnation of the story, which will a little bit relate in the very end. There will be a relation with this curvature tensors that we had, but only kind of marginally. So let me try to set up the stage and let's do it in full generality, or almost. So let me start by defining pullbacks of Courant algebras, which is so suppose we have a pullback of vector bundles. Maybe it's not a grammatically correct sentence, but okay, vector bundle. So we have a vector bundle over a smooth manifold, and we have a map M prime from M prime tau. So let's say pullback. Let's suppose that it's probably along a surjective submersion. I might need it for something later. So so far we have a vector bundle and we pull it back. So we get a new vector bundle. Let me call it E prime. So this is really just a pullback E. Okay, if you wish you can switch arrow here. Map of vector bundles. Okay, so suppose we have such a setup. Then we have two vector bundles related by this. I'm stating in this trade just to kind of emphasize that I have these two vector bundles, but I have an identification between them. So, okay. Anyway, we have this, and suppose that we also have a Courant algebraic structure on both. Structures on both E over M and B prime over M prime. So we fix this. So we have this pullback diagram, and we fix and we choose some chronological structure. And we then say that E prime, by this I mean the Courant algebra structure, that the Courant algebroid E prime is a Courant algebroid pullback of E if the Courant algebra structures are compatible in the following natural sense. If for all sections U and V of the thing on the right, we have, and now I will write the only thing that I can write. So we have two sections here, so we can pull them back, and then we can take, for instance, the bracket. Now the bracket of E prime, okay? Let me denote it with a prime. And the natural thing to denote is this is the same as if we would calculate the bracket here and then pull the resulting section back. And there is the same thing we can write down for pairing. We're comparing pairing prime and pairing. So here this is a function on M prime. This is a function on M, but we are pulling it back. So formally it looks the same. It's a little bit more funny for the anchor because the anchor has to deal with vector fields, and vector fields are not natural. They don't naturally pull back. So instead, the only thing you can say is that you pull a section, then you apply the anchor, which in this case would be the prime anchor. You get a vector field on N prime, and then you push that one back. And you want that this coincides. This is projectable, so that you can first of all push it forward, and what you recover is precisely the anchor of the original thing.
You could also say they are tau related.
Yeah. Yes, but I prefer to say it like this. Sort of. But yeah, not tau related is maybe more common word. Like this vector field and this vector field are tau related. Thank you. So now, maybe a word of warning is that this is not a. So you might object this being called a pullback for the following reason that, in fact, first of all, it doesn't have to exist, and second of all, if it exists, then it's not unique, not even up to isomorphism. So Courant, but it kind of is something to do with pullbacks of vector bundles, so that's why the name I should say. So the Courant algebra pullbacks, so fixing a Courant algebra on the right, and tau, the pullback Courant algebra doesn't have to exist. Nor be unique. And the kind of one way to see that the non-uniqueness is that as far as the sections of so sections of this are spanned by sections. So if you pull back all the sections in here, then because the fibers here are the same as fibers here, it follows that the sections of these things span sections of this guy over all functions here. So it's it's that. Which means that knowing how the bracket and pairing work on some spanning set of sections is actually enough to determine it uniquely everywhere. So actually bracket and pairing are uniquely determined by this data. But it's the anchor that's problematic, because you can imagine that I change it a little bit in a way that it still pushes forward to the same vector field. So there's a little bit of, so the problem has to do with the anchor map. There is in fact a set of conditions that you can write that will tell you exactly like how is this classified in terms of what data you have to choose to make this work, but we won't be interested in that. Okay. Just so the moral, the takeaway message is that we have now a way to say what it means that we have two Courant algebras which are related in some sense. An interesting question could be, what does this thing say in the graded symplectic picture? So, yeah, maybe that. Thank you. So, okay, now the second part of the definition. Stated like this, it will be slightly disappointing, but what do you see? You will see. So if we have the definition is that if we have two pullbacks, okay, not use double prime. We have something in the middle, and we are pulling it in two ways. So if these things are two Courant algebra pullbacks, then we say that the two Courant algebras that Courant algebras on the side are Poisson-Lie dual. Courant algebras E prime and E double prime are Poisson-Lie T-dual. Now, okay, maybe an immediate question that some might have is like, why? Well, duality seems to suggest that there is something that, you know, you have a vector space and you go to a dual and then you go back. In this case, there in principle you can have many pullbacks. You can have a continuous family of different pullbacks. Note that here I'm also, as opposed to the remark, now I'm changing the data they have. It's tau prime and then tau prime. So anyway, so there is lots of ways if you have a Courant algebra in the middle how you can construct pullbacks. Potentially there is many of them. So why do we call them dual? Well, the reason is that it comes from some like standard example in which the case there was a natural way to construct two examples and it generalized the stringy notion of T-duality. We will see that later on. Okay, so far just accept this as a sort of semi-interesting definition, but just, if I have two, I call them dual. Okay. Oh yeah, to put in more random names, this thing is called the spectators. This is manifold of spectators. I'm not sure if people call it like this, but by the way, there is a, if you are looking in literature, there is things like Poisson-Lie duality without spectators. It means that this is the point. Poisson-Lie duality with spectators means that this is not the point. Explain.
If M is a point, so we take a pullback from quadratically algebra.
Yes.
Okay. What does E prime look like? Is it easy to?
E prime. Well, it will be the M prime times the quadratic algebra. It will be our main example later on.
Okay, sorry.
Yeah.
Yes.
Well, in the second half. I mean, yeah. Yeah. In fact, the case with the point is surprisingly interesting. So that's we'll get there. Okay. So far, okay. So we now know. We now have a sort of relation of bare Courant algebras, like nothing. No structure on them. So remember now that we were studying this setup when we were putting a generalized metric. So this was an endomorphism. Okay, we had these two things that were two interesting fields with which we were playing the game. One of them was called generalized metric, and this was an endomorphism. So vector bundle map which squared to the identity and which was symmetric. And then there was sigma, which was an everywhere non-zero half density. And so now what I want to study is whether you can pull these back, whether you can transport them alongside Courant algebra pullbacks. So first observation, I will phrase as a lemma, but it's kind of obvious, is that generalized metrics for sure you can always transport. So generalized metrics can always be transported transported along Courant algebra pullback. So that means that if you have a if G is a generalized metric on E, then we can pull it back using this tau, and this is a generalized metric on E prime. Okay, so this is this is really obvious. It just says that because this thing was a bundle map, so this was a fiber-wise endomorphism. So every fiber of the manifold on M, we had a linear map from the fiber to itself, and since by pulling back the fibers on the left are really the same as fibers on the right, then we are automatically bringing these endomorphisms on back to M prime. So, and you don't need to check that these conditions hold, but they do because they are just point-wise conditions. So this is very easy. What's more interesting is what happens with half densities, because unfortunately half densities don't pull back nicely. I can explain that right like this. So remember what half density was? It was something like, one way to look at it is that it is something that if you square it, you can integrate it because it's a density. That's one way to look at it. And so it's like a square root of the bundle of densities. And the bundle of densities, remember, is kind of, if the manifold is oriented, then it's the same as top forms. So half densities is, you can think of them as like square root of top forms. And claim is that top forms don't pull back along maps of manifolds for the simple reason that if you pull it back, then if your manifold has different dimensions, then pulling it back, if it was a top form, it won't be a top form anymore. Because top form refers to the dimension of the underlying manifold. Like, if you have a map from a 7-dimensional manifold into a 2-dimensional manifold, and you pull a top form from this 2-dimensional thing, then it will be a 2 form on the 7-dimensional manifold. So, yeah. So that's the whole thing. So there is a nice way how to deal with this. Well, there is two nice ways. There is one way is to replace half densities by so-called divergence operators, and we might have mentioned it at some point earlier on, but I kind of wanted to avoid doing that. But let me just say the word, that there is a framework where you can generalize these pairs to pairs of generalized metric and a so-called divergence operator. And divergence operators do nicely pull back always, so those are actually better for these purposes. But I wanted to stick to this one, so let me now explain how to deal with this stuff. How do we pull things back? So, you get half density. Okay, so let E prime be a Courant algebraic pullback of E along now. So what we are going to do is that we are going to pull back the half density, but it won't be a half density, so we'll just multiply it by kind of the remaining, well, by the difference of the half density bundles. Okay, big picture. And if I would have something that's, let's say, pronounced a product, two manifolds, M and N, then half density bundle, now to call it half density bundle of M, half density bundle of the product is the same as product of these things. By this I really mean that you, okay, there's a map to M, there's a map to N from this product. And if you pull back the half density bundle here, you don't get a half density bundle here, but the difference is precisely the half density is here. Okay? To see this, you just think of top forms. If you have a product of two manifolds, then the line bundle of top forms is the product of two top form bundles. Okay, so okay, now for the definition. So suppose let me make this into a definition. So suppose I is a fiber-wise half density, so I need to use new words. i.e. it's a family of half densities defined on one of happens is on the fibers of tau. Okay, and here I should draw a picture. So we have some Courant algebras, but for now we only need to talk about the basis. So we have there's a map from m prime to m. So think of it as m is something like this, and m prime is some, I don't know, some object like this, and there's a map between them. And each point it has a nice free image. So I assume some niceness of this map. So various points that will have various free images, which I call fibers of the map. And I want to have a chi defined on each one of them. But they should only be Hauptenspeed of these slices. Okay, it's really a family of Hauptenspeed indexed by these fibers. Okay. And I want to satisfy a different condition. Okay, this maybe requires some deciphering, but it should be in some sense some nice invariance. Oh, you gamma of the. Okay. Before saying this, and let me say what the definition is. Blah blah. Then gamma is called invariant fiber-wise Hall density. Hope this is not too bad of a name. Okay, so now what does this condition mean? Okay, let's try to reconstruct it together. So, yes, so the remark. So, one remark is that what happens if I take this, just to elucidate what this condition says. So let's take this vector field. So where does this live? This thing. We pull this back. E prime. We had a section here. We pulled it back, and then we use the anchor. So now we have a vector. This is a vector field on M prime. So what happens if I push this forward? Well, I know that that's the compatibility of the thing. I know that this is simply the anchor map on the right in here. So it's tau related to the other vector field. Okay, so what does this mean? Okay, so I want to say that this implies. I wasn't really. Okay. I guess if you're going to get confused with what I'm going to say, just think of this as some sort of equivalence condition. I'm just trying to explain what it means. So this condition should tell you that this vector field preserves as some bundle, or distribution even, some bundle, which is the kernel of the push forward. So looking at this map, at each point, there will be some vectors that are pushed forward to 0. Right? So that will be precisely the tangent space to these fibers. And this thing to tell us that this vector field preserves these subbundles. Does it make sense? What should this thing say? You should say that if I have some vector in here, and I let it flow along this vector field, then I should get something that presumably will be at a different point, but it will again be tangential to this thing. Does this make sense what I just said? Well, okay. This thing pushes forward to something. Okay, well, probably there's some diagram to write or something. Let's not do that. Okay, let's. So sorry about this. So the fact should be. So the fact that this preserves this subelement means that the lead derivative of such thing is preserved. But the fiber-wise half densities, they are really half densities on this, so they are kind of like, if you want, it's like determinant bundle of this thing or its square root or something. So it means that. So it means that it should mean that this thing, the lead derivative of this thing, naturally acts on sections of this, on anything like this that is a family of fiber-wise half densities. Because fiber-wise half density would be a section of like determinant line bundle of this thing.
To interpret this, you mean that this vector field, if you flow it, it takes one fiber to another fiber. You don't mean that it actually fixes the fibers.
No, exactly. I don't mean. I just meant what you said. Yes, and does that follow from here?
That seems correct. Yeah.
So
I think if you use the brackets and the compatibilities, you get the equability of the thing on the right. Because they're always compatible with the bracket as well.
Right, but so far all vector fields or?
Yeah.
Do I need that? I thought it was just something, but
Then it's easier.
I have a vector field which, if I push it forward, I get some other vector field.
That's correct.
It means that the flows are, there's a compatibility between the flow
Yes.
on the right and on the left.
Yes. So does that tell me that if I move?
If you're starting at any point in one fiber and you flow along the vector field in the fiber bundle, then you'll end up in the fiber for which if you had instead projected and then flowed.
Yes, I see, yes. So as I flow along this vector field in here on the left, it will be a corresponding thing here. So yes, I see. So if I would flow here and I would flow to something in here, which would correspond to a point in here. If I would flow for something to here, I would also flow to something in the same point, and that's why the vector, if it was tangent, it stays tangent. Some sort of parallel. Okay, thank you. Okay, so now I believe my own argument. Thank you. Good. Checking. Yeah, cool. Okay, so that's just to say that this is a meaningful thing. Okay. Even if you didn't catch all of that, it's not really essential. That's essential. But okay, so now we have this. So what are we going to do with this? So now, if sigma is a half density, so I'm still assuming that we have a Coulomb pullback. So if we have a half density, sigma is a half density on M. Then we can pull it back, and we get something. It's not the half density, it will be sections of some pulled back line bundle of half densities. But if we can multiply it now with chi, then this is now a half density. The half density on M prime. So more or less that if we can find such a thing, actually for that I wouldn't even need this condition. Sorry, that's not really. I'm not using the full power of this definition, I'm just using the fact that if I have a fiber-wise half density, then if I pull back a half density and I multiply it by fiber-wise half density, I get a half density on the thing. So that's this picture here. I haven't yet used this condition. I'm just saying that you can do this, but then the condition enters in the following lemma. Probably. So if we have a connection, D is a connection, Coulomb connection, or generalized connection on E, then we can okay, I lied, I'm going to use in the next lemma. This is preparatory lemma. So first I'm going to say that I can pull back connections. So if D is a connection on E, then there exists unique connection, which I will call tau prime of D on M prime, on E prime, on E prime, such that the following condition holds, such that all U and V we have, if I put tau primes everywhere, so I differentiate pullback section of V with respect to the pullback of U with this new connection, then this thing will be pullback of the original. Okay. So I'm defining this new object. I'm saying that there is a unique set object that this is true. And this is easy to see, but you can try to have a go at proving it. It's very easy. You just have to show that this condition determines actually all sections, not just pullback sections, but you know that because connections, if you know how they act on generating set of sections, you know how they act on everything, and you can show that it's actually consistent, and you can check that the compatibility conditions hold. So there is, it's not a big, issue. But then, what is very interesting is that this following statement, position. So let me repeat. So if E prime is a current algebra pullback of E along tau, and chi is an invariant fiber-wise Alban density, so think about fiber-wise Alban density. Then the assignment that when you are pulling back these two things, this in fact defines the map from Levi-Civita connections. If I start with a Levi-Civita connection for some G and sigma, then when I pull it back, then the claim is that the thing that I get is a Levi-Civita connection for the pullback metric and for this new Hall density. Sigma. Okay, so if I start with a Levi-Civita connection, I have a current algebra pullback, and I have a Levi-Civita connection, and I also have a choice of this invariant fiber-wise Hall density. Then by pulling back Levi-Civita connections, I again end up with Levi-Civita connections, which will be for the pullback metric and for this thing, for this new pullback thing. But note here that this map, it doesn't use chi in any way. So in fact, it follows that like if there is two or more different chi's, and there can be, then actually the classical Levi-Civita connections induced by them actually are the same. So in particular, if there are more possible chi's, then, well, okay, this is just, okay, if I have chi1 and chi2, then the corresponding things are the same. I mean, this might look strange. That's the only reason I'm emphasizing it. But the reason for that is that the Levi-Civita connection doesn't kind of use the full information of what's in these slots. It uses slightly less information. So if you change this to a different chi, then actually it turns out that that information is not used in. Yeah. Okay. This is just to confuse those that were not confused and unconfuse those that were confused. Okay.
So here it's just that we have a map. We don't know anything, like if it's injected, surjected, nothing.
Not a priori, but wait.
Okay.
Some of this could be. Wait. If it's properly injective.
Maybe if it's unique, then
Which one?
we wrote that they exist unique.
But what he meant was a match, like from here to here. Like, can you have two different things? It's right. Yeah, that can. Wait. Yeah. Only one thing. That is one thing. Yeah, it kind of smells that it's injective. Definitely not surjective. Probably. Yeah, no, it's not surjective, but at least if I add some this surjective version, then probably it's injective. Yeah. Yes?
I think I might be missing the point of what we did with the chi. This is how we used
Very
it
good.
to, you know, to define the actual models. It also will be pullback.
Well, at this stage, I guess the point was just so that I could say this, that the pullback Levi-Civitas, you get Levi-Civitas for some other.
But so what is so special about it? So if you have a harvest satisfying the indirect condition.
You mean what's so special about this condition? Yes, so that you will see that now improve because as opposed to all previous statements, I'm going to prove this one.
Oh.
Yeah. Today is the day. So first, as you know, the proofs that are the things that we know are true. So what does it mean that it's Levi-Civitas? So Levi-Civitas, I remember that there were some conditions. One of them was that the torsion of the connection was 0. The other one was the connection preserves symmetric. And the third one was that the connection preserves half density, where this was defined in some specific way. And this was actually, this was, this is the same as divergence sigma is divergence, it's trace of the, whatever. So there is, so first thing is that how is torsion defined? Torsion is defined in some relatively simple way. We have two things. On the expression we can write that makes this actually a nice tensor. And just by the definition of this pullback, you can see that you see that the torsion of the pullback connection is the pullback of the torsion. Sorry. The pullback of the torsion of the pullback connection is the pullback of the torsion of the connection. So okay. So the first part says that if I pull back T of D, then this is T of tau star D. Did I call it tau star D? Yeah. So yeah, so this is, I'm just saying that this is kind of, if you look at that, if I would pull back the whole thing, then I can always go with my pullback inside. That's what this thing says on all the arguments. And I can, if I pull back a bracket, then it's the bracket of the pullback because I assume that the pullback was a Courant pullback. Okay, so I'm saying that this is not interesting. Like there is this. This one is similarly trivial. It's just tau star D. This was 0. Tau star D acting on tau star G is really the tau star of DG, which is 0. So all just works nice and well. The only thing to check is the last condition. That's where we use the okay, this is good. So what about this? Does the pullback connection preserve our new? Will it be compatible with this half density? Let's calculate it. Now I will drag the formula to no one first formulate it. The u of sigma was defined to be the Lie derivative, sigma minus 1/2 sigma trace of the U. That's how the connection was defined on the problem. And then I can actually simplify this. Okay, I will rewrite it this way. So, okay, so let's calculate this thing. So we want to differentiate this new Hall density along this new connection, along some direction. But we know that, so I want to put something here, like some section of current logic rate. But the connection is significantly linear in this slot, so I can just as well put here any pullback connection. So for all U of E, because I know that such connections they actually span the whole E prime. So it's enough to just check it here. So if we show that this is 0, then we are good. So now I can just start kicking this until yields. So definition, this is the Lie derivative of respect to rho prime, because now we are on the pullback thing, of tau star U, of chi, tau star sigma, minus 1/2, chi, tau star sigma, and then trace of our connection, which is now T star D of T star U. And I'm tracing it over this argument. That's what I said there. There's this free slot, and I'm tracing it there. So well, here I am using. Oh no, I erased it. Okay, so the condition that chi was an invariant fiberwise thing precisely tell me that if I just look at the symbol, that it means that this thing annihilates this chi. That was what the condition was saying. So I can take chi out. Here is where I use the condition. Okay. I'll take chi out. And then I have something like this. Now the only thing to argue is that actually in here. Okay. Here I'm taking a trace of an endomorphism on E prime, so this is trace over fibers of E prime. But since that endomorphism was because of this condition, that should be the same as pulling back the trace of the original. So sorry, this is maybe too fast, but I'm saying that instead you can easily persuade yourself that this is just the trace of Lie of U. Trace over E. And then the final thing is to realize that because you are differentiating something that you pulled back, and you are differentiating it along something that is compatible with the original thing, then after a little bit of staring, it should be difficult to see that this is actually the same as this one. Sorry, I don't want to really go into that much more details, but these are the steps you need to think through. And then it holds, because then you can take tau star out, and you get precisely the thing assembly into the Lie derivative. On the right, on E. The connection on sigma, which you know was 0. So it's, as these proofs usually go, it's just you're just dragging this thing along all this chain of pullbacks and everything.
And so, how uniquely is the chi density defined by this property?
Good, very good question.
Does it always exist?
No, it doesn't always exist. Good, okay. So good, but it's something I should have actually reviewed. So how unique chi is? Because I already said that if you have more chi's, then they lead to the same class of Levi-Citta connection. So they're kind of not really. The important question for answering whether you can pull Levi-Citta, the important question is really if there exists some. If there exists one, it doesn't matter which one you take, you always get this statement. So how unique it is? So suppose that you have two different ones, then they will have to differ by multiplication by a function. I probably sorry, I should have probably, okay, I already erased this. I probably should put somewhere that you want this chi to be non-zero everywhere. Because I want it to map, I want, okay, it's hidden here, but like this thing needs to be an invert everywhere non-zero Hopf density, so this better be as well. So sorry, I should have put a condition that it's everywhere non-zero. Okay, so then if I have two of them, then I can, there are sections of the same line bundle, so I can just compare, they have to differ by multiplication by a function. So if chi1 and chi2 are both invariant, then so is the ratio, then what the condition? The condition was that this thing of the pullback of u on the ratio has to be 0. Why am I saying this? Okay, sorry, let me say it differently. Suppose chi is invariant, when is any other thing I can write as exponential function times chi. When is this also invariant? What is the condition invariant? So what is the condition for f? F is a function. And the condition, well, the condition should be this is just the lead derivative of E on chi, so it should act by Leibniz. And I know that it kills chi because I assume invariance, so the only thing to check is if it kills the exponential, and that thing should be how they act on exponential is the exponential times the action on the function. Okay. The question is when is this 0? That's the question. This thing is not 0. So what does this say? This says that the function f needs to be invariant under all such things. So it's the same thing because I'm differentiating a function, so I can just well say that this is the vector field acting on f. So, okay, I'm not sure if I can say it better than this. So what this thing says is that if I have, so I have a section U, which is a section on the right. I pull it back, and then I use the anchor map, and then I get some bunch of arrows, and they will look like this. So they will, in principle, they might be quite horrible. But there's one thing you know is that those arrows will always push forward to the same. They are projectable, they will project to the same arrow. So does this mean that? It doesn't mean that the function is a pullback. No, it doesn't. So I'm saying that the function needs to be invariant along these arrows, so along these directions. Okay, so yes, it's probably some horrible condition. But in a special case, for instance, when I would, for instance, if e.g., if the original anchor was 0 on the right, for instance, if I take this to be a point, as Jan was suggesting, and this thing is 0, then the condition is that, okay, it's still not that easy, I guess. Okay, yeah, well, but the point is that depending on, well, okay, you can, in the very stupid sense that you have two Coulomb algebroids and they both have trivial anchor, even the pullback, and the other one, the condition is that any function is good. So actually, then all possible cars are actually automatically invariant under that thing, if one of them is. Sorry. Oh no, sorry. I guess that case the very invariance condition was void. Okay. In either case, depends on the situation, but it seems that there is not. It's not. It's further. In general, it's very far from being unique. There can be like various degenerate setups where you can have all sorts of weird behavior. So yeah, the condition is well. This is invariant as well if function is constant along these things. Yeah, sorry, I didn't really answer the question, but okay. So I guess the answer is that it's probably complicated. Any further questions? So, again, maybe a remark for experts, like if you know about divergences, so in this course I decided to not talk about divergences too much. I think we probably defined them, but we didn't pursue them that much further because I wanted to focus on this Hall density case. Because that's kind of the one where you can write down the action function, all the Einstein-Hilbert action, and all that. So if I would instead work with divergences, which would replace these Hall densities in some sense, then this would be much easier because divergence is always pulled back to divergences. Yeah, that's the end of the statement. But still, the most interesting divergences are those coming from Hall densities. So if you pull back a divergence, it is a divergence, but the question of whether it actually is a divergence associated to a Hall density is then the non-trivial question and it boils to this. So, there is no escape. Is the bottom line in these questions. Okay, finally, okay, now, this is actually the big statement, but here is just a corollary of this preceding statement that the Levi-Civita connections pull back to Levi-Civita connections. So if E prime is a coordinate pullback of E, then along tau and chi is an invariant fiberwise Hall density. Then we automatically get a compatibility of the curvature tensors. Remember we had curvature tensors like the Ricci and the scalar curvature and all that, and they were constructed by, we constructed them by talking about the Riemann tensor and then making various contractions, but the Riemann tensor only depended on the connection. So, and we know that connections transport and they're nicely behaving under these pullbacks. So this thing is just, so it's automatic then that the following calls that if you start with a Ricci tensor for some G and sigma, this is constructed using some Levi-Civita connections and then some contractions using metric or something. You know that connections pull back and all these contractions also pull back, everything just pulls back, and this thing is the same as the Ricci tensor constructed using the pulled back Levi-Civita connection, which is simply the Ricci tensor for the pulled back data. So, in this sense, you can say that the Ricci tensor is natural with respect to pullbacks in some sense. So, like pulling, and the same for scalar curvature. Scalar curvature for some data, pulled back, it's the same as the pullback, as the circular curvature for the pulled back data. Okay, and this follows immediately from the previous statement, just because Ricci and scalar curvature were constructing using Levi-Civita functions. So nothing to prove. And this is kind of the core of the Poisson-Lie T-duality observation. It was first observed in some complicated way, and of course we developed the complicated stuff before, and now we just have this as an easy corollary. So, okay, so why is this so awesome? So in particular, if we have a Poisson integral pair, Poisson-Lie T-dual pair, okay, so with this picture with these two wings. And supposing that chi's exist on both sides, for both for E and E prime and E dash prime, and supposing that, then starting, we can start with any generalized metric in half density here, and then we'll produce, by pulling back, some data, but with G prime and sigma prime, namely these guys, that's the sigma prime. And they will also produce some data here, G double prime and sigma double prime. And we know that the Ricci tensor for this is the pullback of the Ricci tensor here, and the same Ricci tensor here, the pullback of the Ricci tensor here, where the Ricci tensors coincide in the middle. So, starting with G and sigma on E, you can produce G prime and sigma prime and G double prime, sigma double prime on E prime and E double prime. And we will have that Ricci, if one Ricci vanishes, so we will have this, if and only if it vanishes on the other wing, double prime. Why is that? Because they are both just pullbacks of the same. Because they are both pullbacks of Ricci. Yeah, I guess I'm realizing that formulating it like this, it sounds like a trivial statement, but probably, okay, in the examples you will see that what is happening typically is that inside we really have something very silly like a Lie algebra over a point, and here we have some interesting geometric setups. For instance, on some groups or something, or even something much more general. And the point is that you can construct some natural geometric data here, and one of them will have vanishing Ricci, if and only if the other one will have vanishing Ricci. And that's a very non-trivial statement, especially if you forget that they come from the middle. Of course, after developing all this heavy lifting, this seems to be like and it is just a trivial statement, consequence of what was said before. Okay, and also we have the same for the scalar curvature. So yes, so to truly appreciate the power of this, we will look at examples. But before that, let me just say that maybe remarks. So far this thing here was compatible. There is just some sort of statement saying that if there is a vanishing Ricci tensor on one side, then it vanishes on the other side. But more generally, if they don't vanish, then you have compatibility with the Ricci flow. So also, this automatically gets compatibility of Ricci flows. Okay, so pictorially maybe, if I have this pullback, and I have some space of, this is space of, let's say, generalized metrics, and half densities on E, and we have a corresponding space here. Now this space is bigger because this, remember that this pullback, we defined it in a way that the map was surjective submersion. So this thing was something, and this was a bigger space dimensionally. So this is something bigger, so the imagine the space of metrics on there is also much bigger. So this is on E prime. Now what this pullback procedure gives us, it tells us that we can pull things back. So if each time you have a data here, you can pull it back. So there is a sort of, I guess there is a map like this, the pullback. And the claim is that this map is compatible with the Ricci flow. So what was Ricci flow? It was, if you remember, that was a sort of set of differential equations for this pair of data, which really corresponded infinitesimally to some arrows in here. You know, this arrow is the Ricci. Integrating those, you get the Ricci flow. And so what this statement about pullbacks says, or implies directly, is that this map preserves these arrows. So Ricci flowing something here is and pulling it back is the same as pulling it back and then letting it flow. So this map is nicely compatible with that. Of course, there will be some locus where you won't reach by pulling this back. So this thing will only talk about the stuff that happens for this, or on the image of this map. It's whatever. And if you would have a second wing, if you would have a second quadrature, then whatever flows here would also automatically flow on both sides, and they would stay they would still stay pulled back along the flow. Okay, so that's one claim. And the second claim is that all of this generalizes vastly. Well, let me not just say much more generally. There's a more general version of this thing. So if the starting thing which we pulled back, if E was in fact equivariant, according to the definition we had last time, so if there was some sort of nice action of the group on the original current algebra, and then if you assume under certain conditions for the metric and under certain compatibility conditions, for sigma and G, so, okay, sorry, this picture is getting a bit small, but this was the setup. We had these two pullbacks. And now if this thing was G equivariant, then so since the fibers of this thing are the same and the anchor maps are compatible, these things also should inherit a G equivariant. So there will be a G equivariant on these pullback objects. And we need to study this. Okay. Let me not go into detail. Maybe we need to do a little bit of adding a little bit of data. But anyway, if you have such a thing where you have these groups acting, then you can make a reduction of these things on the side. So you can. So you can reduce this using the group G, and you can also reduce this one. And the claim is that if the data of G sigma here was nice, then it also descends to these things. So you will have some, I don't want to write it. So you will get some geometry data, and this layer will be in the same duality statement. That if Ricci vanishes here, it will vanish here, and vice versa. And this thing is called equivariant. Poisson-Lie T-duality, or some people call it dressing causes.
So one way to get a Poisson-Lie T-dual situation is to start with a J equivalent.
I will say that next.
So this is like another step. So
this is another step.
Okay. So this is like twice equivalently reduced.
I think so. Yes. Yeah. Yeah. This is a different step. This is a more general. Okay. Yeah, sorry. don't really like how they forward what to do. I think you have to. Maybe this is not natural. You need to supply some data to say how it's here or something. No, we don't. No, sorry. No, there is no data yet. Sorry. Once you such a map means that there is a map from the Lie algebra to sections of here. So if they just pull back a connection here, sorry, there is no data. It just works as it is. Okay, this is just to say that the setup I presented was fairly general, but there is yet a more general version that concerns reductions. And in the simplest case, for instance, or in one of the simplest cases, going in this more general setup, you can recover some nice Poisson-Lie T-dual pairs on some double cosets. So you have like a group modulo a Lagrangian subgroup or isotropic subgroup modulo further on the other side an isotropic subgroup or something like this. So for those who know, like in this way, how one can recover things like eta deformations of the ADS5 or this 5 supergravity backgrounds and stuff like this. It fits into this framework. But yeah, it's just a remark, so we won't talk about that. So instead we will talk about examples. Okay. So what is the easiest example of this, and why is this whole thing called Poisson-Lie T-duality? Examples. Okay, let me start the proposition. That's the quickest way how to phrase this. So, suppose we start with the following simple geometric data. We have a quadratic Lie algebra. So Lie algebra with an invariant pairing. So let this be a quadratic algebra. And H inside G, a coisotropic subalgebra. Okay, I forgot if we probably defined coisotrope. Yeah, I think we definitely did, but let me remind you that this just means that the orthogonal complement is contained within H. That's what coisotropic means. Now, let G be a Lie group, integrating G. And suppose H is H inside G is a closed subgroup integrating H. Okay, so here I was very sneaky and I secretly put a condition here which says that, I mean, if you have a subalgebra, a Lie subalgebra of an algebra, then you will always, and you integrate one of them, then there will be a unique connected subgroup integrating the smaller one, but in some strange, bizarre cases, it might happen to be not closed. So I'm just imposing that it's closed. Like, I don't know, something with Torah or something, for instance. So let me just be proper and sneak it here as a condition. And the claim is that then there exists a unique Courant algebra pullback structure on this simple diagram. So we start with our G and regard the Courant algebra over a point. If you remember, Courant algebra over a point is the same as the quadratic Lie algebra. Now we take a map from this group quotient G mod H, and then we do what Jan was saying. We pull this back. So we have a unique map to the singleton, to the point. And what is the pullback? Well, as a bundle, it is a product bundle. It's just this space times this vector space, which is the Lie algebra. So as a vector bundle, it's kind of a boring one. But we are now claiming that we can equip this with the Courant algebra. We can put the Courant algebra structure here, which makes the pullback of that one. And we can fix, because this in principle doesn't have to exist or it doesn't have to be unique, so we fix the anchor map. The anchor map rho prime given by the action of the algebra on the quotient. Okay, let me draw a picture for this one. So the takeaway message is that if you start with this very simple purely algebraic data, model disclosure condition, but that's just technicality you're supposed to ignore. So if we start with a Lie algebra, which is quadratic, and a coistopic subalgebra, then you can craft an interesting Courant algebroid. Well, you can craft a non-interesting one, which is the algebra over a point, but you can also craft an interesting one, which is a Courant algebra over this manifold. Now, what do I mean by the last part? So, what do I mean by that the anchor is so what does it mean action of G on this thing? So remember that the group G acts on itself by left multiplication. So in particular, this descends to the right quotient, okay, by left multiplication. So this descends to whatever cosets that we have when you model on the right. If you model something on the right, it doesn't matter, you're acting on the left. So there is a well-defined action on this coset space. Now, differentiating this, we get an action of a Lie algebra. What does it mean to have an action of a Lie algebra? It's an infinitesimal action of the Lie group. So this is the same to say that we have a map from G to vector fields on this thing. Okay, that's what it means to have a Lie algebra action, which is a homomorphism. So this is a homomorphism of Lie algebras. Now, what does it mean to have a homomorphism of Lie algebras? Or just, what does it mean to have a vector space? What does it mean to have a linear map from a Lie algebra to vector fields? It means that you give me a Lie algebra element, and I give you a vector field along the whole manifold. So in particular, at every point, I have a linear map into the tangent space. So this is the same thing as to say that there is a map at every point. Let me write it like this. There is a map from this tangent space. Okay, so bounded map. So this is the same way for every point on M, I have a map from G to that tangent space. That's the same to say that I have one map of this form, which is precisely what I want my anchor map to be. It's supposed to be a map from here to tangent space here. Okay, so that's what I mean by that. Okay. In case this was slightly cryptic, now let me just refer differently. So in other words, we have a Courant algebroid structure on this a priori silly looking bundle, such that on constant sections, right? So the bundle is a product bundle, so it makes sense to talk about constant sections. So on constant section, you recover the bracket and the pairing on G. Oh, sorry, this was simulation. Okay, I'm not going to prove this. There's multiple ways how you can prove this. There is a fairly straightforward way, and you can write down the formula for what the bracket looks like, and then you can just check that it satisfies the axioms. Then you will see that it wasn't clear, probably, it's not very clear why I need the coisotropic condition. So my claim is that the coisotropic condition comes from the fact that I want the result of Courant algebra to satisfy Jacobi. Or more precisely, You might remember, depending on whether we covered this or not, I forgot, but there probably was a claim that the electric current algebra, the kernel of the anchor is coisotropic. And the kernel of the anchor here corresponds to the action of the stabilizer of this, so it's H. So it better be coisotropic. So, that's just a comment. So, well, once you believe me that this is a quantum algebra, then that's a relatively simple observation. This is always by this I mean the result. The result in quantum algebra is always transitive. Why? What does transitive mean? Transitive means that the anchor is surjective. But now the anchor is simply this action map. And this thing here is a transitive action. Hence also why it's called transitive algebra. So yeah, it is, so anchor map comes from here, so it is transitive, it's surjective. So this is transitive, and furthermore, it is exact if and only if dimension of H is 1/2 dimension of G. Again, simple proof. This is just, if you remember there was a statement before that the way to recognize an exact current algebra between transitive ones is to the base should be half of the dimension of half of the rank of the bundle, and that's just this condition. So, in particular, this is a pretty cool thing, but it says that if I take the proposition and instead of taking coisotropic, I take Lagrangian, then I'm claiming that I can construct a nice current algebra on here, which does look kind of easy. It's a product bundle, everything. But in fact, this thing is an exact current algebra, and we know that for exact current algebras, you can identify them with T plus T star of the thing, and that's kind of not super obvious that actually you can identify this thing up there with T plus T star. But it's true nevertheless. So this is part of this Poisson-Lie T-duality is interesting because it leads to some things which are not super obvious. And and another final lemma says that both of these lemmas refer to that proposition. Okay, so the second one says that there exists an invariant chi. So when does this chi exist so that we can pull back our densities? It turns out that in this context there is a nice characterization, and it says that such an invariant chi exists if and only if the subalgebra H is unimodular. What does that mean? It means that for all elements in the Lie algebra, the trace of the adjoint of that element over the algebra is 0. So that is an easy condition. Finding examples satisfying this condition is non-trivial, but interesting. Okay, so to conclude, I guess, so then thus, call it what we have learned. So thus, for any two Lagrangian, let's say, let's be specific, Lagrangian, for any two Lagrangian subalgebras of a given quadratic Lie algebra, we get a pair, Poisson-Lie T-dual pair of exact current algebra. Okay, because if I have one G at two different ages, then I can play this game twice, and I can construct two pullbacks. So yeah, this is how we can produce lots of these dual pairs. And what's the simplest example of this construction? So what do we want? We want to have this quadratic Lie algebra, and we want to have two Lagrangian subalgebras. Now, in the simplest example, you can ask more. You can ask that they are actually transfers. So such that, so suppose H intersection H prime is 0. Well, in this case, then G, H, H prime are called a Manin triple. Or Lie algebra, the same thing. Have you done any Lie algebras on one of the other courses on deformation quantization? No? And well, okay, then but never mind. This is a cool concept that is particularly interesting also in the context of deformation quantization. This is the semi-classical limit of a quantum group. That's right. Or a special case.
H would be the same classical.
Yes, sorry. Like this structure is the same as H with a bivector, with a bracket, satisfying convolution. H being a Lie algebra. And that thing is a semi-classical approximate limit of the quantum group. So anyway, so then the corresponding manifolds that I get are G mod H and G mod H prime, but in this particular case when there are transfers, you can actually, at least locally, identify this thing with the other group and vice versa. So what you get in the end is that you get two Poisson individual Courant algebroids, one living over this and one living over that, and they are dual in the above sense. And these two things, this is what is called Poisson-Lie groups. Or if you want to dual pair of Poisson-Lie groups. So this was the original motivation for this kind of stuff. That there is that if you have two, so there is a notion of Poisson-Lie group, which, if you haven't seen it before, it means that it's a Lie group equipped with an extra Poisson vector that is compatible with that. Namely, it's multiplicative in a certain sense. Yeah, or we want to say that the Lie map, the multiplication map, is a Poisson map. Or there is various ways to say this, I guess. But there is a sort of nice interplay between Poisson geometry and Lie theory. And these such groups typically come in pairs. And those pairs are a natural candidate for this kind of Poisson integral framework. So this is where it gets its name. So these original two dual setups, they were happening on these two Poisson groups. Okay, and now the simplest and silliest example that you can do, simplest example, and silliest in some sense, because I will take it up again. You can take this G to be two copies of R, and you can take the pairing to be, the pairing will be pairing this thing with this thing, so they will be kind of isotropics. So you take this Abelian algebra, and inside it you can take these two some algebras. One of them you take it to be this, and the other one you can take it to be this. Just one copy and the other copy. Just smash two isotropic things together. With a pairing in between, and then then you can take G to be S1 times S1, and H will be S1, and the H prime will be the other S1, this one and this one, and then the quotient you will get, so you will get a duality between a circle and a circle. So this doesn't look very exciting so far, but that's because I haven't yet talked about metrics. So, because remember this Poisson integral, the interesting point was really about that if you equip the thing in the middle by some algebraic structure, then you can pull it back, or by some. So if you equip the Courant algebra in the middle, which in this case will be this guy over a point, if you equip it with some generalized metric, you can pull it back and construct some sort of interesting structure that they will be compatible. And if you will pull a generalized metric here and here, then it would result in two metrics here, and those metrics, that's my final picture, they will kind of recover the usual Poisson integral string theory where you have like two circles, one of them radius r and one of them is radius 1 over r. So if add sorry, this is a bit vague, but if I add generalized metrics to make this actually a non-trivial statement, then you should be getting some dual geometric setups, which in this case simply correspond to this kind of constant metrics on the circle, but in one case this is a circle radius r, and the other one is radius 1 over r. So this is the origin of, this is CF T-duality in string theory. So in this way, although a bit briefly, I try to sketch that this is the way in which this framework of Courant algebra kind of vastly generalizes this concept of T-duality in string theory. Yeah, if there were more time, I could have sketched a way to produce. So this is an example without spectators, to link it with the previous description, because the Courant algebra in the middle, if you remember, because there would be a point, so this would be like the no spectator case. There's a simple case to upgrade it to the case with spectators using some principal bundles replenishing corresponding triangle class. So this is what Martin was looking before. So that would be like, I don't know, there is a way to do that, to produce like much more exciting things. But yeah, I think I will finish here.